Okay, so now I'm going to go through the chapter 4 with you. Just let me organize things. Okay, so now you must be looking at my video on the side as you wished one time, and to the slides that I'm going to share with you. So chapter 4 is going to be about, if you want, the combination of the two things that we have seen before. So the vibration and rotation of diatomic molecules. So we're going to study the case where the molecule is doing both motions. So it's vibrating and rotating, which is usually the case, if you want. Obviously, we're going to study the spectra and see how things will show up. Well, again, the same sort of questions. Obviously, yes, quantum mechanics, we have seen that. So we're not going to actually go through any classical treatment of the things. We already knew that from chapter 2 and 3, that we need quantum mechanics. And we have defined, if you want, the spectral numbers and spectral terms, sorry, for the vibration and the rotation. Now we're just going to combine them. So usually, as we always start, we just get a first look into how things would look like experimentally speaking. Experimentally, in contrast to what we have seen in vibration alone and rotation alone, we would see in the spectra of rho vibration or rot vibration, that's the way it's said, we will see sort of band. So if you want, you would see this red line, which is an envelope, if you want. Obviously, we won't see the envelope. We will see just the spectral lines, but they will be looking as there is a band. And this sort of band is characterized by one specific thing, that there is a gap relatively large in between two sides, if you want, two set of bands or lines, sorry, on the right and on the left. Now, what we will see, so we call these branches, the right side and the left side, we call them branches. So they are formed by spectral lines of absorption, let's say, or emission. And obviously, we talk about absorption most of the time now. And they form sort of a band. Now, what we're going to explore is, again, same sort of things. What is the origin of each spectral line? And now you can tell, basically, that this will be a transition, either of rotation or vibration. And the second thing that we need to know is, from a spectrum, to what values or to what expressions correspond these spacing between lines. So the middle lines, the middle spacing, the large one, and the small ones. And are they different on the left, on the right sides? That's what we will see. Now, just visually speaking, if someone is asking, or if the questions come to your mind, how would a molecule be rotating and vibrating at the same time? Well, here's the question, here's the answer. It's like if you want an harmonic oscillator, or obviously we have seen that it's going to be the treatment of an anharmonic oscillator, but for visual reasons, think about an harmonic oscillator, something that it's actually, well, one of the molecules just behind me, just think about them doing this, and at the same time, they are vibrating, rotating, okay? So this will create these sort of closed waves, if you want, very similar to the de Broglie sort of wave of the electron wave function, but well, it's not the case here. It's just moving like that, and you will see that the distance will be changing due to the vibration. Now, what is really important to keep in mind, that the scale of energies between vibration and rotation is different. Meaning that if you take again the example that you are in the class, sitting on your benches, You are the molecule, and the placement of the benches corresponds to the energies. Now, each row in the class corresponds to a vibration level of energy, and each seat on the row corresponds to a rotational level of energy. So you could actually, with the same level of vibration, just change seats on the same row, because the change of seats is less energy change than changing the row completely. And that's how the molecule would react. So we could find ourselves in a certain state of vibration and then doing the rotations movements. However, there are rules or selection rules for these transitions. And this is what we will see. So we will see that we should respect the selection rules of vibration, which means delta V should be plus or minus 1. But at the same time, if you move from one row to another, you cannot just go to any seat in the new row. Going to a new seat, so to a new level of rotational energy, should also respect the laws or the selection rules for the rotational energy transitions. That's the whole idea. So the total energy is the rotation energy plus vibration energy. I won't go into the classical details of things. But yes, the important part is that we have two cases. The first one of them is an approximation, because it's actually not real. The two cases are the following. The first approximation considers that the two motions are independent, which means that the vibrational motion and the rotational motion, physically speaking, are totally independent, which is, you can appreciate, I think, that it's cannot be really the true case. They should be related. But as a first approximation, we are going to treat the model of called the vibrating rotator. So we consider that the two motions are independent. This will forces us to take some considerations on the spectral terms, which simplifies things. Now, the second model, or the more real model, would be when there is an interaction between the two motions, which means that if the vibrational energy exists, then it will create a certain effect on the rotation and vice versa. Then we will see that. So in the first approximation, where we consider that the two motions are totally independent, so simply the energy in this case, the total energy of the molecule, would be the energy of vibration plus that of rotation. So if we are going to write that as we did in the previous chapters in terms of spectral terms, now you know that, we just simply add them. So in terms of nu bar, so in terms of centimeter minus 1, we would just write that E is Hc GV plus Fj. So GV is the spectral term for the vibration, and Fj is the spectral term for the rotation. Now we call this sum as T. Okay, so T is G plus F. Obviously now we know, or you know, what the term for G is. So G is omega E V plus half minus omega E x E V plus half over 2 plus half squared. And this is the G term for the anharmonic oscillator, which is the real case. That's what we've seen in chapter 3. Plus Fj, which is Bj, J plus 1, plus Dj squared, J plus 1 squared, which is the term coming from the correction due to the centrifuge distortion. So it's just like a summary, if you want, of chapter 2 and 3. And this is why I would like you to focus your study on this chapter. So we add the G term and the Fj term. Great. Now, look that, well, this is, we are taking the example here. That's what we said before. What you see in here is a harmonic well, but that's not the thing. This is what I said, that you notice here, I'm drawing the levels. I'm not sure if that's very clear on your side, but this level here and this level here are a little bit bold in red. These two, if you notice with the numbers, they correspond to V equals 0 and then V prime equal 1. So V prime, just to say it's a different level. It's not a derivative. And you notice that the rotational energies, so we can have different rotational states. The molecule could actually rotate with different energies while still vibrating at the same level of vibrational energy. So V can still be equal 0. So this gives a certain energy of vibration, but J can change. Physics speaking, then you are now on the same row in the class, but you have different possibilities to sit on the same row. And obviously the same case when the vibrational energy gets increased. So we go to V prime equal 1, then you also have different levels of energies of rotation. Okay. Now, transitions. It's very easy. It just requires simplicity on one side, focus, and cleanness. So you need to draw things clean. Otherwise, you might get lost. So please don't draw things just like lines, etc. Make things, get yourself a small ruler, and if you have colors, that would be great. Okay. So as you know, as I said, we can move from one vibrational level to the other. So from one row in the class to the second row just after it. Why just after it? Because we know that for vibrational energies, the selection rules is delta V equal plus or minus 1. Now, obviously, as you can read in here, this is with the highest probability. Okay, but this usually what usually happens. So we move from one row to the one just after, delta V plus 1. So there should not be any transition of the rotational vibrational of the combination of motions. There should not be a transition of energy unless we go from one vibrational level to the one just next after it. Okay, good. Then we have changed the row in the class. But now the question, to which seat in the new row can I sit? So which rotational energy can I get into? Well, obviously, you cannot move to another seat unless the difference of delta J is plus or minus 1. But then you could say, wait a second. If I was sitting in the first row, so I have V equals 0, my energy of vibration is V equals 0. I'm sitting in the first row, in the first seat. Now, if I want to go to the second row, then delta V equals plus 1, that's okay. But can I go to the first seat in the second one? No, because if you go to the first seat in the second one, then your vibration, then your rotational energy would be delta J equals 0. You actually have to change your seat by one step. So you go from the first seat to the second seat. So this delta J now equals plus 1. So now you have satisfied the two things, delta V equal plus 1 and delta J equal plus 1 in terms of absorption, obviously. Okay, now you can say, okay, wait, what if I was sitting in the second seat on the first row? So in V equals 0, you were at J equal 2. Where can I go then? Well, now you have two options. Because if you go, first of all, if you go from J equal 2, so if you go from the second seat in the first row to the second seat in the second row, it's not possible. Because you haven't changed your rotational energy. You haven't changed your placement on the seats. You should change it by delta J equal plus or minus 1. But now notice, you are absorbing energy to go from the first row to the second row. So delta V equal +1, that's absorption. Okay. But since you are in J equal 2, and since the rule of selection is either delta J equal 1 or delta J equal +1, or -1 and +1, then what you can do, sitting in the first row, second place, you can either go to the second row, third place, and in this case, delta J will be +1, or you actually can go from the second place in the first row to the first place in the second row. Then delta J equal -1. Both are satisfied. And in this case, delta J equal -1 is not emission. Why? Because what governs your placement initially is V. You have moved up in energy, but you changed the seat to a lower one. That's all, in rotation-wise. And this is explained, if you want, with this diagram. And this is where I really need you to be neat. Well, you seem to be, but just... Okay, so the red lines correspond to the rows in your class. This is the level of vibrational energy, V equals 0 and then V equal 1. However, for V equals 0, you have different seats, so different J. J equals 0, so V equals 0, J equals 0, or then V equals 0, J equal 2, V equals 0, J equal 4, etc., etc., etc. Now, when we get to the second row, so V prime equal 1, then the same. You have the first seat, second, third, fourth. So V prime equal 1, J prime equal 0, V prime equal 1, J prime equal 2, etc., etc. Now, what are the transitions in terms of absorption in this case that are accepted? As I said, first of all, what you should notice, from the point of view of vibration alone, you could go from V equals 0 to V prime equal 1. But J would be always equal 0. So you go from J equals 0 to the second level, J prime equals 0, and this is not allowed. You can't go from one row to another and keep your seat. You can't. And this is not allowed. When I say it's not allowed, it means that at this wavelength that corresponds to this transition, there will be no line. And this will show up later on, this gap. So this gap corresponds to the transition that is not allowed between the two levels of vibration, which correspond to delta J equals 0. Now let's look to the branches. Now, obviously, as I said, if you go to the second seat, you can either go to the -1, so you go to the first seat in the second row, or +1, then you go to the third seat in the second row. Both are okay. Now, if you were in the first row, if you were sitting at the seat number 3, again, same thing. You can either go to the second row, place number 4, so delta J equal +1, or you can go to second row, delta J equal -1, so you go to seat number 2. And this creates the two branches. The first branch is all the choices that you can make to go with delta J +1. So you increase your position on the rows. So your rotational energy go with the transition of delta J +1. And the second branch is the one where you choose to go with delta J equal -1. But always you are going to the second row in terms of vibrational energy. So look, the first one is going from V equals 0 to J equals 0. To go with delta J +1, you need to go to V prime equal 1. That's normal. But G prime must be equal to 1. Well, something is wrong in here. Okay, just they are not corresponding very nicely, but that's the idea. And then from Vj equal 2 or J equal 1, you need to go to V prime 1, J prime equal 2. If you are at the level V equals 0, so first row in the class, J equal 3, third place, you can go to V prime equal 1, second row, and J equal 4, etc., etc. So always you are going from one j to the other j that is higher by one step. Now, what about the other ones? Well, the other one is when you actually, one note. If you are initially sitting at the first row, first place, so j equals 0, the first movement that you can do is only to go to j plus 1. Because your initial place is j equals 0. You can't actually go to the second row and sit at j equal minus 1. It doesn't exist. But you start having the second option of going with delta j equal minus 1 when your seat is j equal 1 in the first row. Then you can go from j equal 1 in the first row, so v0 first row, j equal 1. You can go with the option to reduce your j, so you go to v prime equal 1, j prime equals 0, and then you have gone from the first position or the first seat in the first row, sorry, from the second seat in the first row to the first seat in the second row, and this is delta j equal minus 1, and same for the rest. So if j equal 2, so v0 j equal 2, if you go to the option to reduce your seat, then you go to v prime equal 1, j prime equal 1, okay, etc., etc. Now, this will create two sets of bands. Bands that corresponds to delta j equal plus 1, and other that corresponds to delta j equal minus 1, but both bands correspond to delta v equal plus 1 in absorption. Obviously, between these two sets of branches, there will be a place where no line appear because it's not allowed. And this corresponds to v0, j0, going to v prime 1, j prime 0. Okay, so that's the idea. Now, mathematics speaking, for vibrational transitions from the level v equals 0 to the level v equal 1, delta v in absorption is equal plus 1. So obviously, we calculate the difference in the spectral term, g, for the vibration part. So g v minus g v equals 0 gives this relation. Obviously, if v equal 1, so if you are doing the first transition, well, v equal 1, and this, you get this. Well, this we call it omega 0. Omega 0 here is what? Is the movement, is the energy difference, is the spectral energy difference between v equals 0 and v equal 1. So if I go back here, it's this dashed line of energy. Because notice, this is from v equals 0 to v equal 1. So we call it omega 0. So this will immediately point your minds into the thing that the spectral line in the middle of the gap should correspond to what value? Omega 0. Because this is the difference of energies that should have done a transition at the spectral line omega 0, but this transition did not happen because it's not allowed. But the position of it, so if you look to the gap and take the middle of it, this value should be what? Omega 0. And I notice here, the transition of pure rotation corresponding to the following couple is forbidden. V equals 0, j equals 0 to v equal 1, j prime equals 0, delta j equals 0 is not allowed. But the difference is between v equals 0 and v equal 1, and it's given by this. Okay, so now there will be a set of situations. They might look complicated because it's a lot of writing, but you can nicely just draw a diagram on your book or your notebooks. We are now in the first approximation, rigid vibrating rotator, which means that no influence between the two motions. But in this case, we also have several situations. The first situation is when we consider that there is no centrifuge correction. And the second situation would be when we consider that there is a centrifuge correction. This will just play with the terms. So This is the first approximation, no interaction, so the B is constant because there is no centrifuge effect. Then delta J equal +1 in absorption would give us the delta F of the spectral terms equal to 2BJ +1. We have seen that. And delta J equal -1 will give us -2BJ. Now, these two bands, the red one here, it's called the rich band. So all the transitions corresponding to delta J equal +1 give a set of lines forming a branch or a band called the rich band. Well, because you're just gaining +1. And the green line here corresponding to all the set or the set of all transitions of delta J equal -1, it's called the poor band. So that's what I'm writing here. For the rich lines or the R band, delta F would be equal to this because delta J equal +1. So again, I can repeat, it's as if here you have, if you want, rotational spectra alone. Each band is like a rotational spectra alone. So the spacing between lines would be governed by this 2B thing. Same thing in here. But the whole thing is rotation and vibration. This is why you have the gap. And from the equations, you can tell that if I can determine from a graph the middle position of the gap, I will get ω0, then I will get these values. And then from the lines of the sets, branches, I can get B values. And I have everything. However, how does it work? To determine the wave number of the spectral line, that's what we want. For the case of the poor branch, so now I'm looking into delta J equal -1. So for the poor branch, it's the lower frequency, so it's the side on the left. What we have is obviously a delta V equal +1. It should be delta V +1 in case of absorption, obviously. But we are moving one step in V, in vibration. But then for the poor band, it's where the delta J equal -1. But notice that, and that's very important, and that's where the confusions can start getting in. For the poor band, for delta J equal -1, you can't do this unless you start from the second place on the first row. So your J starts from 1. There is no delta J equal -1 starting from J equals 0. It's not possible. And we have explained that. So if I look now into delta T, which is the spectral number of the whole thing, which is the sum of the both, it's going to be delta G from V equals 0 to V equal 1, plus delta F from G to G -1, with the condition that this G starts at 1. So if you just take this one, delta V0 to V1 equal ω0, that's what we have seen just in the slides before, and this one gives us -2BJ. And we call that the spectral lines, if you want, the spectral lines of the poor band. So this is the spectral lines that will appear here. Each line of them will have a spectral, so new spect, index P to say it's the poor band, it's the poor side, that is equal to this. ω0 -2BJ. Now, obviously, the question that I can ask you, and that would be very easy to see, what would be the very first line of the poor band? Well, the very first line of the poor band should correspond to the very first transition after the non-allowed one, right? So this one goes from what? From j equal 1 to j prime equals 0. So j is equal to what? 1. And this what gives us that the first line that corresponds to the transition from j equal 1 to j prime equals 0 actually is just omega 0 minus 2b. So now immediately, when I have a spectra or spectrum, the middle of the gap will give me omega 0. And the position of this spectral line, the first one, would be omega 0 minus 2b. So if I have this value experimentally, and I have the middle of the gap, I have omega 0, and I have the new bar of the first line, then I have b. If I have b, I can get to I can get to u, I can get to r, as we did in the rotation. Right. Now, what about the rich band? Well, the rich band is when we have, again, delta V equal plus 1. We change the row, but delta J equal plus 1. And this we can do. Actually, we can do this if J equal 0. Because if you are sitting at the first row, you can go to the second row. You can go to the second place in the second row. So delta J equal plus 1, J starts at 0. So if we do the same calculation, we get the new bar, the spectral line, the value of the spectral line in centimeter minus 1. For the rich band, each line of them, it's equal to omega 0 plus 2bj plus 2b. But for the very first spectral line in the R band, so I will do it again, for this very first line in this rich band, well, this line happens for the first allowed transition after the gap, which goes from j equals 0 to j prime equal 1. So j equals 0. So I put j equals 0, and I get that the first line of the rich band corresponds to omega 0 plus 2b. So you can immediately see now, I hope it's written in here, yeah, it's written in here, that in fact, if you take the difference between the spectral line of the first pole band, or the first line in the pole band, called P1, and the first line in the rich band, called R0, 0 here because J is 0, but 1 here because J here cannot start unless it's 1. And then you can see that from this diagram nicely. It's much more explicit than the one before. Then the difference between them is just 4b. So actually, it's not only that I can get the middle, but now even the width of the spacing is 4b. And as we have seen in the rotation, so it's as if you want, the blue lines, it's just like one set of this, it's like a spectrum of rotation. And since we have ignored until now the case of centrifuge, so we considered it's a rigid rotator, then the spacing between them is constant and is equal to 2b. You know that from chapter 2. Same thing for the other side. It's nothing different, just also delta j's. Again, it's 2b. So now we have in this model, in this approximation, well, we can read any spectrum. Now we get into the second case, always with the first approximation. So we are still in our diagram that probably you must have drawn it. So we are in the first approximation when there is no interaction between the two modes. And in this first approximation, we said there is two things. It's either rigid rotator, so there is no centrifuge, no D, or the real case where there is a D. So there is a centrifuge correction. And in this case, well, just the expressions, if you want, of delta F changed, as we have seen before. So delta F for delta J equal plus 1, taking into account the centrifuge correction is 2bj plus 1 as before minus 4dj plus 1 cube. That's the centrifuge correction. And in case of delta j equal minus 1, which will be the pore lines, it's minus 2bj as before plus 4dj3 j cube. Again, we do the same thing. For delta j equal minus 1, so now we are doing the same thing, but again, I repeat, we are in the situation of first approximation, so we consider no interference between rotation and vibration, and we consider the case where the rotator is real, so there is a centrifuge correction. And we do the same calculations. So for delta V equal plus 1, delta J equal minus 1, this will give us the pore bend lines, but it starts at J equal 1. So if you do the difference, well, this one remains omega 0 because we are going from V equal 0 to V equal 1. And now we go from J to J minus 1. So from 1 to 0 if you want. And this is going to be the spectral line of the pore bend in this situation. And this will just add a correction. So it's going to be omega 0 minus 2bj plus 4dj3. Now, obviously, again, if we are in this consideration of the model, and you are going to seek the value of the spectral line for the first line in the pore bend, well, this line starts from j equal as 1, because it's delta j minus 1. So we'll go, the first transition starts from j equal 1 to j prime equal 0. So if you put j equal 1, you will see that the first line on the pore bend is omega 0 minus 2b plus 4d. Now, same thing for delta j equal plus 1. So we look now at the rich band, just adding the centrifuge correction. So we do the difference, or delta t, which is delta j and delta f. Now from j to j plus 1, knowing that j starts now at 0. Then what we get is omega 0 plus 2bj plus 2b minus 4dj plus 1 cube. It's the same, but we added a correction. Now the first spectral line on the set of lines corresponding to the rich band would start at j equals 0, and then that will be 0 goes here, and here we have omega 0 plus 2b minus 4d. Now again, if we look into the first line here and the first line here in the rich band, and we do the difference in between them, we see that the gap will become 4b minus 8d.